Hello everyone. In today's lecture I am going to discuss quadratic form. So it is from Advanced Engineering Mathematics book, edition 10 by Erwan Kreisig, or section is 8.4. Now quadratic form. So transformation to principal axis. So by definition, a quadratic form Q is the component of x vector from x1 to x1 is a sum of n square terms. So it can be written as that Q is equal to x transpose A XOR in double summation from j1 to n, k1 to n, ai jk, xj and xk. So here is called the coefficient matrix of the form. So we may assume that A is symmetric because we can take off the diagonals. How we do that? Let's see an example. Now let's consider an example 1 here. So it is written that if you look at this as a quadratic form, if we multiply on both sides of x1 x2, it becomes 3x1 square plus 4x1 x2 plus 6x2 x1 x2. So we can add these two, and this is not a symmetric, so look here, but this then can be written as 4 plus 6 or 5 plus 5. So if we use 5 plus 5, we can easily write this into a symmetric form. So how we convert matrix into symmetric is very simple. So if you want to matrix as C, matrix as a symmetric, so what do you do? Just take the alternative values, that is jk and kj, and take the sum these two coefficients and divide by 2, so it will become 5 again. So this is the way you can convert any matrix into a symmetric one. So from here, when you apply the multiplication, you get the same result as we have in previous quadratic form. So this means that normally A is a symmetric, can be written in form of a symmetric matrix. Now let's consider a theorem, and theorem says that if you have a symmetric coefficient matrix A, so has an orthogonal basis of eigenvectors. So hence, if we can take these as a column vectors, we obtain a matrix X that is orthogonal, so that X inverse is equal to their transpose. So this is the benefit of having an orthogonal matrix. So thus we can use this for transformation here. Now for example, if we have A is written as x d x inverse can be written as x d x transpose. Now here D is because X is a matrix which has the column of eigenvectors, so D becomes the diagonal matrix with at diagonal values are the eigenvalues of matrix A. So if we substitute this in equation 1, so it becomes equation 2, that is x transpose x d x transpose x. So from here, if we do a substitution, coordinate substitution, we say that for example x transpose x is equal to y, that as we know that x inverse is x transpose, so from here we can write that x inverse x equal to y, or y is equal to capital X times x is equal to capital X times y. So this is equation number 3. Now if we substitute this equation number 3 in equation number 2, from here we can have a relation of Q in terms of coordinates y. Now the good thing here is that if we do this transformation, so we come up with y transpose dy. So from here, as D is a diagonal matrix with eigenvalues, so we can easily write that Q is equal to y transpose dy, and first eigenvalues multiply by y1 square plus second eigenvalue is y2 square up to number of coordinates which are present in the quadratic form. So this is equation number 4. So this equation tells us that if you do the transformation, you can easily transform the coordinates into a new one if you have a is a symmetric matrix. So because of orthogonality, you can easily write that new transformation is actually the multiplication of eigenvalues with the coordinate squares is the new quadratic form. Now we look at the theorem, which is about the principal axis theorem. So what principal axis theorem says that Principal axis theorem says the same thing. If we have a quadratic equation and A is a symmetric matrix, so we can come up with a new coordinate principal axis form or canonical forms using the eigenvalues, that is lambda 1, lambda 2, and that we see in equation number 4, where we rewrite this q in terms of y. So this is all about the principal axis theorem. So principal axis theorem is basically, if you have a symmetric matrix A, you have to calculate the eigenvalues, and then you can rewrite the quadratic form into a new coordinate system, and that is known as the principal axis. So from here you can find the direction of principal axis by calculating the eigenvectors of those axis. Okay, now look here. For example, how we do that, let's consider an example here. So example says that transform to principal axis in conic form. So find out what type of conic section the following quadratic form represents and transform into principal axis. Now the question given to us is that q is equal to 17x1 square minus 30x1 x2 plus 17x2 square is equal to 120. Now as we know that we can write into it's a matrix as a symmetric matrix. From here, because 17 is the axis value, we have a 30, we have to divide it by 2. So from here we can rewrite A as, look here, for x1 coordinate we wrote here 17, for x2 we wrote the other diagonal as 17. Now 30 is divided by 2, it becomes minus 15, so it becomes an A matrix. So similarly we have a coordinate of x1, x2. Now from here the next step is to calculate the eigenvalues. Now we have to write the characteristic equation for the A matrix. It becomes 17 minus lambda square minus 15 square equal to 0. From here we come up two roots as the two eigenvalues. One is the 2 and second one is the 32. Now using these two eigenvalues we easily calculate the new coordinate system and also the eigenvectors. Now new coordinate system becomes, as we know from the theorem, that it becomes the eigenvalues times the y1 square. Similarly second eigenvalues times the y2 square. So this is the quadratic form. Now what type of conic section we have? We have to use the equation that as the q is equal to 128, we have to submit here q value here. So it becomes 2y1 square plus 32y2 square equal to 128. Now if we divide it on both sides by 128, so it becomes 1 divided by y2 square 8 square. So as you know that there are two different values here with the square term. So because if these two are same, so this means that it is a circle, but here these values are different, so you have a 2 radius here, so it represents an ellipse. Now let's see the orientation of the ellipse or directions of the ellipse. So for that case we have to calculate the eigenvector. So how to calculate the eigenvector? We use a characteristic equation, that is A minus lambda I x equal to 0. Now just put the first eigenvalues here and calculate the value for this vector x. Similarly put the second value and calculate that. So I come up with two eigenvectors. Now I put the second and these two eigenvectors. First one for 2 is 1 over under root 2 and 1 over under root. Similarly minus 1 over under root 2. Now to calculate the orientation, so this is the principal axis. So to calculate the orientation, what we have to do, we have to divide the second bit divided by the first one and take the tan inverse. Okay, so from here it becomes 45 degree, here it becomes minus 45 degree. Okay, now the orientation. So to take the to calculate the axis, so we have to put x and y. This is, I can take the first column and put the second vector in the second column and multiply by y. So to calculate it, this becomes the principal axis, and this is the coordinate transformation from x1 to y1 and y2, or from y1 to x1. So the orientation becomes 45 degree. So this is all about to calculate the transformation to principal axis using quadratic form. Thank you.